Okay, here is the explanation of the project. The project is a simple project. It's like the continuation of the Turtlesim Buster. My goal here is to spawn turtles and move from a starting point to a goal, but the mission is to try to avoid other turtles. So there will be turtles in the field, one central turtle, and they will try to get to their goals, but without touching too much each other. So the organization of the folder, uh, the project folder is like that. You will have uh, include files from each specific task that I'm doing. For example, the PID, the frame broadcaster, the static broadcaster, and the turtle functions. Also, we have a launch file and the same with the source codes of these include functions. These functions will be used in example in the post broadcaster, in the simple planner, and in the world broadcaster. Also, you will have a package .xml to uh, include in the project, explanation README that will be on GitHub, and also some application that you can launch on the on the package. So another thing to understand here is the project is not complex, but I'm trying to explain more about the structure of the projects, because when the project start to grow, it will be complicated to do it on a simple file. It will grow a lot and you will not be able to navigate between the files. So the main goal of the project is the structure, how to structure projects. So on the source folder, you will see that I have another folders for all my include functions, but uh, my CPP files that are on the root of the source folder are the nodes. So that's my thinking. If I put on the source folder CPP files, that will be the nodes, and the other ones will be functions that will support the nodes. Another thing to note here, uh, there's let's explain the CMake list for better understanding. I have a minimal required version of CMake that is 3.02. If it's not this version, it is a fatal error. This is the project name. All the package needed to all the necessary package for the application. For example, we are using TF2 and Turtlesim, the geometry message for running the application. And the interesting part is here how I'm doing how I'm adding the libraries. So for adding libraries, you have to use this CMake uh, construction for, in example, the turtle one. If I'm trying to include the header file and the source file, I will put it as static library and include the header file and the source file from its locations. So what happens when you build? It will make a .a file that will be linked later to the necessary CPP file that is loading this library. The same is done in the TF2 broadcaster library. So here is the header file and the source file, and also from the frame broadcaster, here is the header file and the source file, also the PID. And finally, for making the executable, we only make the nodes, the goal, the post, and the simple. The goal broadcaster, the post broadcaster, and the simple planner. And finally, For the simple planner, we will link these libraries that we will be using. The library named Turtle, TF2 Frame, and PID. The post broadcaster doesn't use any library, any additional library. And the gold broadcaster, obviously, because it's a fixed frame, and we will be using the TF2 static frames, TF2 static library. I mean. So that finished the CMX list. Let's view the launch file. The launch file is simple because everything is repeated. I have launched the Turtlesim node, also my main planner for each turtle. The format is the turtle name, X position, Y position, and the rotation. So you repeat this to any turtles that you want to be in the field. Next, we will be trying to broadcast the pulse. So we will be using the package name that we are trying to execute and the post broadcaster node. Another thing to note is that the value of the string of the turtle name is the same as the turtle that we put on the simple planner node. That's important. On the final part, we have the static frame broadcaster. We will be broadcasting the one goal for each turtle, and also the central turtle, because will be not moving, it will be broadcasted statically. So this turtle has a name, turtle1 fixed, for broadcasting the turtle name, and the other ones are the same name but underscore goal. So you will put the X position, the Y position, theta, roll, pitch, and yaw values for each turtle that you want to static broadcast the goal, and you're done. Another thing to note here is that let's see the package. Okay, here are the packages that we're using: the geometry message, ROS CPP, TF2, ROS, TF2, Turtlesim, and also we make the build sports depend and the execution depends. For the in example, the PID controller, we have some functions like the constructor gets the constants of the controller. For example, kx is for the distance, kz is for the angle. And next, this function will update the controller, and this one get the errors because we will try to pause the tutorial when an error of distance and angle will be reached. Those are private values for reserved for the error and the values of the PID controllers. Here's the class definition of the functions. We initialize each one of the variables for its manipulation. Next, we will do a PID control over the transform stamp, because when we have both transform, it's pretty easy. Just for distance, it's compute the Euclidean distance between the translation, and for the angle correction is the arctan2 of the Y position and X position. Also, we are making incremental error and differentiated error computations. And finally, we store the values for the error because we will need on the next function, that is the error. This one will only populate back the error values to make on the main application stop or continue doing the PID control. For the frame broadcaster, the same. We have some initialization values for the frame. We have also to look up transform between frames. That's what this function is doing. And we need a listener. We have to initialize this listener with a buffer. Also, this variable is to make the transform stamp to be calculated. So for the transform stamp broadcaster, we have the constructor that does nothing, that just only initialize the listener with the buffer. And we also have the function that look up between the source frame and the destination frame. Frame 2 is the source frame. Frame 1 is the destination frame. And we are trying to look up this transform at real time. So that's why here is ROS time 0. Okay, for the static frame broadcaster, sorry. For the static frame broadcaster, we have this class. The only things that it does is initialize with the parent and child frames. If you want to change it on real time, you will not rely only on the constructor. You have to set it the frames for each situation, and it will broadcast depending of the transform stamped divided in translation and rotation. Also, because I am doing argument requesting the argument from the argument vector in the main function, I will change the translation and rotation vectors from string to float, and finally get a vector tree for next compute the broadcaster. Those variables are for static broadcasting and stamping it, and those are the parent and child frames. So for this one, we have here the class definition. We only initialize the parent and child frames, and again it's the same as the constructor, but if we want to broadcast it in real time, we will need to change it, the parent and child frames to calculate, because those frames are dynamic. We will try to do it from different frames in the field, and this function will broadcast the message to TF using the translation and rotation vectors. This one is just to transform string to float, and the same below, string to float the argument vectors. So probably these are not good function definitions, because in the future we will try to change it, but at this time that's what I need, so we will keep it right now. For the turtle functions, we will try to do a constructor for the turtle. We will be also spawning turtles on the field given the pose and the name. We also set the pen off or on given the name, and those functions right now are not working very well, the kill functions, but you will not need for this application. Those ones are the node handle, the client for the spawning, and the client for the killing turtles. This one is only the turtle name. So for this class definition, we need to specify the turtle service that we are trying to be called. So if we are using publishers, subscribers, services, that will be here. Right now I'm just spawning, so it will be fine to be just only spawn here. This is the spawn function. As you see, given the pose and the name, we will try to wait for the service until 10 seconds, because when we're starting Turtlesim, and because I'm on the virtual machine, we will try to do it a little bit laggy, my emulator, so I need to wait at least I think 3 seconds, but I put 10 because some virtual machines of others could be uh, less permissive than mine. And finally, we set the pen off. These functions by the turtle name try to set the pen off or on depending on the boolean value. And those functions I have to review because they are not working right now. The kill function, given the non-name, just killing myself as saying that myself I am a turtle. And this one is for killing another turtle that is not myself or could be myself. So the nodes right now that we are using. Okay, let's go with the gold broadcaster. The gold broadcaster node just only use the function that the classes, I mean, and the functions of the static broadcaster, because a goal is a static frame. It will not move. So we will report to Word this goal, and we will try to broadcast given the translation and rotation. And finally, we will spin. So you are seeing that the application gives a little bit simplicity if we make classes. The post broadcaster, those are the dynamic broadcast of the post. We are just using this function that subscribes to the main function. I mean, that subscribes to the turtle post, and finally we post. The post will be called by the callback, and we will be broadcaster. It will be broadcaster by sending the transform. And the main file that is the simple planner. The simple planner, uh, it has its constant definitions. If you want to change the minimal distance to less, and multiplicator, I will try to explain it later. It's on the main code. Those are the values of the PID for distance, and those are the values for the PID between the angle correction. This is the node rate, and this is the buffer of the command velocity. This function is just to calculate the Euclidean distance. It's below. It only calculates the Euclidean distance given the transform stamp. And here I think we can start explaining the application. Those are only variables needed to refer on the application. Let's try to go first. We will retrieve the turtle name and the pose. Also, think about this as one turtle, not 8. We'll later try to spawn a turtle and disable the pen of the turtle. Also, we'll spin the main loop given the node rate that is 10. And we initialize the controller with the constants of the PID for distance, the constant for the PID for the angle, advertise the turtle command for this turtle only. This thing initialize the start and the end times. At the beginning, it will be 0.1 from now, just to compute the later the delta time and be 0.1. But first, we will look the transform between this source turtle and its code, compute the delta time, and sometimes it gives me a small value, so I'm clipping it to 0.1 because SP node rate is 10. I'm clipping it to 0.1 because the differentiative error, it will be growing a lot if I do not do that. We will update the controller. Again, we will start measuring the time, make and a stop if the threshold is below from distance and from angle. And for avoiding turtles, that's a part that I hard coded here, but I think I could be doing this better in another way on the launch file probably. But right now it's hard coded are all the turtle names. So you will see there's a turtle on the left, on the right, up, down, and another random locations that I put on the launch file, and also the name of the turtle one uh, fixed frame. So we will look over each turtle, but we will only execute the controller of the avoidance if the current turtle is not the current name is not the current turtle. So for this turtle and the others, we will do a collision avoidance. We'll compute the distance. If the distance is some sort of minimal, less than the minimal distance of one turtle and another, we will try to look the transform, make a repulsion of angular velocity and a repulsion of distance. So this multiplication that was above defined is a fraction of the distance. So if we are near the total, we will be doing it fast, a fast rotation. If not, we will do a small rotation of the angular velocity. And we will try, if we are near, we are trying to going back a little. So that's our application, and finally we will publish the message depending. No? If we are right on the goal and we don't have any obstacles, so the application will finish. If not, it will try to move the goal and avoid turtles. So basically, and that is the application. It's pretty simple, but as you see here, it's more like organization. So you have this CMake list that will aid you to know how to add libraries, static libraries. Let me show you. So when you build a static library, it will go to this folder in the devel lib. It will be constructed these static libraries, and finally we will be linking by doing it on CMake. So that's all. Okay, let's just run the application, but it's on a separate video. So you will put Rust launch, Turtlesim simple planner, that is the package name. And finally, you will put the simple planner.launch file that is here and try to launch the application. So you are seeing that it's far from perfect, but at least does the job. The turtles try to avoid each one, so they don't collide as default is on Turtlesim. And that's all. Let me just put you the RQT graph. Let's see, RQT. So it will be looking complex because let's see first the TF3 because it's more simple. So the TF3 will have the turtle positions reported to the warframe, and this is the middle turtle, the default turtle of Turtlesim, and those are the goals of all the turtles. So the TF is pretty simple. Now let's look to the node graph. It's more complicated because R8. I recommend you to view the repository because there's a simplified node graph of 3 turtles, one fixed and 2 others that will be navigating around the world, the micro world. So let's see, instruct spatial node graph. Here is, it looks scary, but it's not as scary as it seems. So the only thing that is doing the application is uh, broadcasting all the transformations to TF static if there are goals, and to TF if there are dynamics, and each planner is acting at itself and commanding each turtle of the Turtlesim simulator. So we will have a planners, main planner underscore Y, X, and Z, W, and planner down, up, down. For the central turtle, we don't have a planner because it's fixed, and that's all. So the node graph looks scary, but at least if you see in to three turtles only, you will see that it will not look as scary at all. It's pretty simple. Let's try to view it here. Here you see the it's pretty simple. It's the same as plain as before. Just uh, it's only a simple planner between the statical and the